Okay, so thank you. Welcome. This is the second lecture on machines, drives and applications. So hopefully you all turned up to yesterday's session with Mark Sumner. And as you'd expect, we're co-teaching this module. So I'll go over a little bit about the teaching split and what we cover. But fundamentally, we have two people. So I convene the module and I do about half the teaching. So we have me teaching on this module, and we also have Mark Sumner, who's going to be doing the drive system aspects of the module. And then we do also have one further person teaching. Later in the course, we'll have one of our newer academics, Tianji Zhu, who's going to be coming along, who's going to be teaching a specific teaching week around switch reluctance machines towards the end of the course, and is also going to be running the machines coursework, which I'll introduce in a little while. So hopefully you're all in the right place. This is our module. So this is an autumn module, 3082. This is my contact details. So I think the line at the bottom is there. This is something I'll try and highlight throughout this course, is get in touch if you've got questions. You're in third year by now, so hopefully a lot of you have got this, but a big part of the structure, a big part of the course is asking questions, whether it's around the talk material, whether it's around the problem sheets, whether it's around other things. So make sure you're getting in touch, make sure you're asking any questions. You can contact me via email, but I also have an office in the Coates building, so you're welcome to come along. As long as I'm not actively involved in some other meeting or something, I'll be happy to help you. So feel free to drop in, very happy to help you with this stuff. Best way to contact me is by email. Teams isn't really a good way to contact people. It just tends to get lost in the noise of hundreds of team messages we get. So email is probably the best way. So what are we doing? So again, you've hopefully been to that previous session, you're in this session. So we have our two key teaching sessions. We'll have two 2-hour slots a week. So this week has been split equally between myself and Mark, so we can both introduce our sides of the course. In future, you'll find most teaching weeks actually break into one or the other. So we'll typically take a whole week to introduce a topic, or multiple weeks. And if you look at the teaching schedule, which is on Moodle, you'll see that that does actually switch back and forth between us, but ultimately we'll be covering different aspects and we'll make sure everything is sort of covered. So you'll have one or the other of us in every week, and then Tianji will be covering our final teaching week. The other thing you will see in your timetables later on is online sessions. So these online sessions are there specifically to support the coursework. So those are there to support the machines coursework, because you'll be using some simulation software you won't have used before. Those are there from week 6 onwards. So those will be appearing in your calendar later on, but don't worry if you're not seeing those just yet. Those are only there once that coursework starts up, and Tianji will be running those to make sure you get coursework support. How we assess this module? So we have a 2-hour exam, 8 questions, 40% of your module, as well as two 30% courseworks, one based on simulation and the other based on a drive experiment. So our assessment, as I said, we have an exam. So the exam aims to cover all machines topics that we don't assess elsewhere. So what that means is we'll be covering all the things around concepts, applications. We'll also be covering thermal behaviour and reluctance machines. We will cover AC fields and induction machines. There is one subject which we don't cover, synchronous machines. So synchronous machines around the middle of the course is one of the first main machine topics we introduce. So this is your typical synchronous wound generator that you get in a power plant, and also the things like permanent magnet synchronous machines for high power applications. Now we don't cover those in the exam because actually those are the focus of the machine modelling coursework. So we don't want to double assess you, which means that those won't be in the exam. But we'll try and flag these things out as we go along to make sure you're catching up with the topics, make sure you're keeping engaged. And then the coursework. So the coursework on machine optimization via simulation. So that's going to be looking at trying to design, simulate a machine, and ultimately looking at sort of testing and validation around synchronous machines. So it's using the same kind of software as you might use in industry in order to actually look at how you would modify a machine design. It won't be a sort of CAD exercise. You won't be expected to design a machine from scratch, but working from pre-existing designs, you'll be looking at how you pull out those key characteristics and how you can modify certain factors to get different performances. This will be assessed via a report submitted through Moodle. And then you have a drive simulation coursework. So Mark Sumner's probably covered a little bit about that. I won't go into too much detail, but that's looking more at the drive system rather than the motor as a whole. And this is a split you'll see throughout the course. I'll be covering machine topics, as will Tianji for his particular week. And Mark Sumner will be covering most of the drive topics, again, apart from that particular week on switch reluctance later in the course. So there's a main split between me talking about how machines work, how you can characterise and specify them, and Mark looking more at the overall system level and the drives that can control these. So the machine coursework, sorry, there's a typo there, that should say week 5 as well. We've suddenly skipped forward 2 weeks. So apologies for that. But yeah, so this is just outlining that software. We use a commercial machine design software. So this is something that's available through the university's virtual desktop, basically to make it easier for you to actually access a commercial software. The idea of this is you're using something just like you might be using if you go into industry, so that you can use some real industrial tools, get some hands-on experience. And you'll also be using this to actually apply the testing methods. So this is a practically focused module. For all the machine types we talk about, we'll be teaching you how you could take an unknown machine and actually work out its characteristics, and so work out how it'll perform. And you'll be applying those same kind of methods on the simulations. So this is our overall structure. As I said, we have a fairly even split. You'll see some weeks you've got myself, some weeks you've got Mark. So you'll be with me now for this week and next week, where I'm going to introduce some of the basics around machines. So there'll be some material you might have done in previous years, whether you're an MSc in your sort of bachelor's degree, or whether you're a student with us that you would have done in years 1 and 2, and then we'll be building on that as a bit more of a foundation. You'll go with Mark for a week where he'll be introducing the specifications, applications, so trying to introduce the system level side. Then we'll be getting into the actual nitty-gritty of synchronous machines, how they apply, how you'd use them, and introducing that coursework, and interspersing the drives material. So you've got a mix of material, but we're basically going through this course in that structure. You can see we'll be covering a reasonable amount of material. We'll also be pulling in a guest lecture towards the end of the semester, so we'll be aiming to bring in someone from industry who's got a lot of experience in the machines and drives field. So the last couple of years we've had speakers from automotive and aircraft electrification, who are actual sort of working industrial people designing and developing drives. So these people can actually then tell you a little bit more about the actual application, so the actual day-to-day of what they do, and ultimately it gives you a view of where this kind of field can take you, the kind of things this is applicable to. So what are we aiming to learn on this module? So our learning outcomes, so we have these learning outcomes which all sort of tie back to what we want to do with a module. And ultimately the module's around practicalities. So we want to get understanding of the concepts of electromagnetism and the physical principles of behaviour. So this is something that we'll be covering mostly at the beginning, and it's something that you have covered to some extent in your prior studies, but we'll be building on and reinforcing these underlying principles. We'll be looking at classification and distinguishing common types of machines. So this is all about machines and applications. It's about knowing how different machine types operate with respect to one another, but also around applications, how you would specify these machines. We'll be looking at the techniques for how you would do a similar thing around drive technology. So how you could analyse machines and drive technologies and select appropriate technologies for an application. You'll be looking at electromagnetic performance of machines using analysis software tied into the coursework. And you'll also be looking at how you can develop drives and vector control systems. So there's a bunch of learning outcomes, but what we're really aiming for, I'd say the overall takeaway from this module is by the end of this, you should be able to specify machines and drives for typical applications. So we're not really training you to be an in-depth machine or power electronic drive designer. That's something that you might potentially address in further modules. But what we're trying to teach you is to have an understanding and awareness of how you would use different types of machines. So if you go into industry and you have a requirement for an industrial robot or a renewable system or a transportation system, an electric vehicle, you could start to make informed choices around the type of machine you need, the type of drive you need, what are its drawbacks and characteristics, and how you could represent that as part of a larger system. We don't have any recommended textbooks on this course, so we don't demand that you go out and buy a bunch of textbooks. We do have a reading list of things that you might find useful. Everything should be available in the library, so feel free to have a read of them. They are quite useful and they'll all teach the subject in their own way. And this is also another area you can go to get help if you're not quite understanding the material. These all teach the same kind of things, but in slightly different ways with slightly different examples and illustrations of the concept. So all of these could be useful. Then in terms of teaching tools, as I've said, we'll be using some machine simulation. And the way we use this is a technique called finite element analysis. So this is something I'll use to demonstrate some machines concepts in lectures as well as being used in the lab. But the idea of this is it uses simulations of complex machines through a graphical user interface. So it means you don't have to do all the maths and programming yourself. So in its simplest form, this works on something like a 2D slice of an electrical machine. So if we took a fairly classic electrical machine, stator, a rotor, some coils in slots around the edge, it's a very, very simplified model. But what this software does is it takes this whole model as a 2D slice and it breaks it up into individual parts. So they typically use triangular meshes and it breaks it up into a huge amount of different parts in the air gap, in the rotor, in every different part of the machine. So each of these pieces of the geometry is broken down into a small element made up of one material. And it does that because then the internal and very clever software systems can build a huge set of equations that actually represent the electromagnetics of this. We have a very good set of electromagnetic equations that represent what flux density we're going to get, what current flow we're going to get, everything that'll interlink those pieces. So finite element software breaks a model down into a set of finite elements and then solves the huge complex matrix of equations in order to give you a solution. But the reason we teach this is because this is the absolute industrial gold standard. So before this software existed, the only real way to know really exactly how a machine was going to operate was to build and prototype it. Whereas now we can use these softwares to represent machines at a 2D or a 3D level and get simulation results that are very, very close to how they'll actually operate. So it's a very useful tool that we want to introduce because you may commonly be using it. There are a lot of different softwares available and we'll just be picking out one particular software for the coursework, but it gives you an awareness of the overall field and the kind of tools you might have to work with in industry. So that was just a brief introduction to the sort of course and the teaching patterns. So the next thing we're going to get to is talking a little bit more about the fundamentals. So before we get into that, has anyone got any questions about the overall teaching pattern, about what we intend to do? All pretty good so far? No worries. Assuming this decides it's going to open eventually, we might actually have a second slideshow. There we go. Okay. So for the next part of this, we're going to talk about the technical fundamentals and topologies. So we're going to do a little bit of an overview, but first we're going to go into what this builds on. So there's a few things that you should know. Well, as I said, this counts both for MSc students and undergraduates. So these are the things that we know are taught in the first and second year of our undergraduate course, but these are also the things that we expect to be taught on the equivalent sort of BEng course that has led you here in an MSc. So vector representation and calculus, we don't get into massively in-depth maths, but you need to know the basics, you need to know how to use simple equations, you need to know how to use complex numbers. So there's nothing hugely analytical, we're not going to be going into pages and pages of equations, but we need to know enough to handle things in the real and complex domain. The basics of magnetic fields and how magnetic fields operate. So this is something we will recap to some extent. So next week is all going to be about building up on some of these things, but we expect you to have some idea of magnetic fields, magnetic circuits, and how the magnetics of a system operate. We expect you to have a little bit of ability in terms of DC and AC circuit analysis. So DC in terms of sort of overall power, the Ohm's law level, and also a little bit of knowledge around AC circuit analysis, at least when it comes to things like resistance, capacitance, inductance, and things like phase relationships and power factors. So these are all things that we teach in our first year course. So these are the kind of things that you should be reasonably familiar with. And then another thing we will be relying on is some knowledge of three-phase systems. So three-phase systems are absolutely fundamental. Pretty much all electrical machines, certainly all electrical machines above the sort of small domestic size, use a three-phase supply system. And so having some concept of the star and delta connection, what's the difference, active and reactive power, and how the sort of power transformers work will be an advantage. So these aren't things I'm just going to go, oh, you absolutely understand these, but these are the kind of things we're going to build on. And over the next sort of week's teaching, this is when we'll reinforce these concepts a bit. But if you're not quite sure about these, over the next week is a good chance just to pull out your first or second year notes and just go through some of these concepts and make sure you understand them. And ultimately that's because these are the sort of things that give you a grounding in the module. You have to have some basic understanding of things like power flow, active reactive power concepts. And that's just flagging for undergrads where these were covered in our first and second year modules. So power and energy, which I would have taught you actually, and energy conditioning and control. So let's get to the fundamental behaviour for machines and drives. And the fundamental purpose for machines and drives is energy conversion. So if you have a machine and a drive system, that's designed to do one thing. It's to convert energy from one form to another. So in a machine and drive, we need to convert between two domains of work. We need to convert mechanical work into electrical or vice versa. So ultimately, wherever energy has to be converted between electrical and mechanical forms, we need some kind of electrical machine to do that job. And as well as that electrical machine, we very often need some form of drive system to manage and control that. It could be a complex drive, it could be a very, very simple drive. It depends on the application, but we need both of those to some extent in pretty much all applications. Now, when we talk about the machine, we're talking about the physical machine which is responsible for energy conversion. So this is where we're converting energy between electrical and mechanical forms. So we have two key definitions within this, two key subsets. So if it's doing mechanical work, if it's using electrical power to do mechanical work, it's classed as a motor. If it's converting mechanical work into electrical, so usually for energy generation, for transmission or storage, it's working as a generator. Then the definition of a drive is something that is the overall system designed to do the work. So drive is a sort of catch-all term for an overall system. So that can often include the motor, but it could include any power electronics, any control systems. Confusingly, occasionally people will call a power electronic drive as in just the power electronic converter the drive as well. There's a lot of interesting terminology in our field. But ultimately a drive is a system designed to do a job. So that could be the simplest of simple systems. It could be a very, very basic plug-and-play machine, or it could be a hugely complex system with conversion, with feedback, sensing and control. These can get very, very complex depending on the application. So the reason we look at electrical machines is they're the most common and effective energy converter between electrical and mechanical. So electrical machines are the most common energy converter, and they're also the thing that takes the most power of anything on the grid. So 45% of the UK grid, for example, goes to feeding electrical machines. So it's a huge part of our grid makeup, and these machines are doing all kinds of things, anywhere where we need some kind of mechanical power, directly or indirectly supplied. So we have a bunch of applications, and we'll talk about applications after the break, but we have a mix of applications for machines. So we have our very traditional applications. So these are things like industrial drives, pumps and generators. So in the sort of industrial revolution days where we went from simple mechanical drive to things like water wheels, ultimately up to things like electrical drive. So the very traditional driving some kind of load in industry, driving a machine in a factory, operating something. So this is a very, very traditional role for machines, but also things like pumps. Again, for almost as long as machines have been around, they've been used for pumps, from back in the old days when they used for things like sucking water out of mines, to looking at something like a modern building where you've got hundreds of motors all around the place pumping and distributing air around, pumping liquid around various systems. So you have a huge amount of those. And then of course generators. Wherever we have a grid where we have energy, we need to generate that power. And all of that power, with the exception of some sort of outliers like solar, is coming through an electrical generator. So the vast majority fed onto the grid today, whether it's from a traditional combustion power station or whether it's from a very modern wind turbine, is going through some form of electrical generator. But of course these aren't the only applications. As we've moved into the modern age, we get a lot more interesting applications that come across, and this is one of the reasons why it's really worth studying this, because it's also a key driver of careers and a key destination for our students. So things like embedded generation. So chiefly wind generation is a huge thing right now, but also things like electrical and hybrid vehicles, replacing very traditional combustion drives with more modern electrical equivalents, including things like electric ships and aircraft, but also robotics, automation and manufacture. Wherever we build in this automation, wherever we expect some kind of electrical system to have an impact on the world, we need machines there to actually make that mechanical impact happen. So why is this becoming a more important field to electrical engineers? So the first thing is our enabling technology. So power electronics is a huge enabling technology for machines because it allows us to do all kinds of things that we never could before. So before modern power electronics, we were fairly limited in what we could do with machines because we didn't have good ways to control them. They were quite simplistic and they tended to produce simple amounts of power in simple ways. And if you wanted to make them controllable, you had to go to very, very great lengths and have very intricate, elaborate control systems. Modern power electronics and drives mean that you can have a fairly simple system, a plug-and-play type drive, that can give you any torque, any speed within a certain range. So it gives us a huge step change in enabling technology and what we can do with machines. And of course, supporting this is microprocessors. If we have the power electronics knowledge in order to control machines at any speed, we also need the processing, the communications. We need that underlying information and systems type technology to control, to operate our machines and to make sure they're optimized. And then another driver of these is new materials like permanent magnets. So when we talk about synchronous machines, we'll discuss how one of the big things that's actually driven the improvement in electrical machines are new materials, things like rare earth permanent magnets. I say new, they're relatively new in the sphere of machines. But what these let you do is get some really, really efficient machines. So they'll let you make a very compact high power machine so that you can start putting machines into things like cars that you could never really do practically before. But they also let you get very, very high power density out of machines. So if you want to get huge forces, if you want to do some really, really high power jobs, they let you do that efficiently too. So these improvements are leading to some really interesting things. They're leading to higher speed machines. So if we can drive machines faster, it opens up new ranges of applications for them, but it also lets us get more power out of existing machine designs. So our power is proportional to our rotational speed, which means that the higher the speed is, the higher power. We can get higher torque density, so we can produce more physical force from the same type of motor volume. And again, this lets us open up new applications in order to get machines into more places. We do have these new topologies which actually only operate through power electronics. So a lot of the machines we'll talk about are fairly traditional, but things like the switch reluctance motors that Tianji will be telling you about towards the end of the course are a fairly new topology which is entirely reliant on power electronics. So they have some very good characteristics, they have some really good applications. These are the kind of motors that are in most Dyson products, for example. But they do need that power electronics, they do need those controllers to operate. They have no other effective means of operation. They also let you have higher operating temperatures, and operating temperatures are important because it opens up new things you can do with them. So you can have challenges of operating temperature all over the place. It could be that you want to mount machines into the borehole of an oil well, which is at several hundred degrees. It could be you're looking at space operation where you have high temperatures from solar incidents, and also it's very, very hard to get rid of losses. But having machines that can effectively operate at higher temperature is, again, key to open up new areas of application. And then high performance and energy efficient control is a very important one. So getting good performance is absolutely key because a lot of applications like electric vehicles are absolutely performance critical, but energy efficiency is a big part of it. And this is because energy efficiency is a big driver in electrical machines. So I mentioned before about how 45% of the power consumed on the UK grid goes to electrical machines. And actually there are very, very significant and strict rules around the efficiencies of machines, in that any production level machine has to meet a certain efficiency standard. And this is one of the ways that they drive the sort of reduce CO2 emissions, they push for energy efficiency. And this also then leads to all the knock-on effects of seeing things like efficiency stickers on appliances. But the big part of that efficiency is coming from the electrical machine, and the more efficient you can get those, the better. And of course, energy utilisation, and especially now with a sort of energy crisis, with energy prices having somewhat spiralled over the last couple of years, energy efficiency is a huge issue, and the cost of actually using energy, the cost of making products, this all ties in. So if you can increase the efficiency of the machines in your factory by 10%, it's a huge difference, and sometimes it's the difference between staying in business versus making a loss and failing. And then also things like electric transportation. So electric transport, and especially automotive electrification, is an absolutely huge field for this. So all of these enabling technologies, having higher speed, higher torque density, high performance and controllable machines, has allowed us to actually have practical generations of electric vehicles and hybrid vehicles, which is very, very important in that we're pushing for a full conversion to electric vehicles by, depending on which politician you believe, 2030 to 2035. So this is something every automotive manufacturer is very, very heavily invested in, actively working on, not just in the UK but around the world. And then the final driver is renewable energy. So this is something that's massively grown over the last 20 years from something that was pretty much a gimmick and not really any part of the generation grid to something that at times forms the majority of generated energy. So these are all the things that are actually driving this advance. So let's look at some fundamental questions. So we have a few basic questions we're going to ask over this course, some of which are fairly simple and can be addressed now, some of which we'll see as we go along. So the first thing is the basic constitution of an electrical machine. So what defines an electrical machine? What is it? How does it operate? We'll look at why are there different forms. So why do we have multiple types of machines? Why do we have synchronous and induction and switch reluctance? Why don't we just have one best machine that does every job the best way? We'll talk about how do they work, so the underlying physical principles of operation, so how they actually produce force, the mechanisms behind those, and how those can be modified and harnessed in different ways to get different behaviours. This is a key one. How big will a machine have to be to deliver a particular power? Because this is all about application and sizing. And this is one of the things you would very, very commonly address in terms of actual industrial application. If you need a machine that produces 3 kilowatts of power, what you'll find effectively is there are very, very sort of established sizings of the type of machine that will do that, unless you want to go into the high cost, high spec sort of speculative. If you're looking at an industrial machine, you'll find there's a very, very common type of sizing that all ties back to a few key equations that tell you how big a machine is going to have to be to deliver particular power, which is absolutely key when you need to actually specify one, put it into a system or an application to do a real job. What do I need to know to use a particular machine type? And again, these are application type questions of if you want to do a particular job if you said, okay, I know I need to have this particular machine type, what kind of characteristics do you need to specify? What do you need to know about the supply you're putting to it? What do you need to know about how you're coupling it up? How does it need to be controlled? And what kind of limits will it operate in terms of environment, temperature, and so on? So how can I analyse the method of working of a machine type? So this is all about knowing how machines operate, but it's also about representing them and simulating them. So as we'll see when we go through the course, every machine that we talk about has some way that we can realistically approximate it with an equivalent circuit in the electrical frame. And the reason that's important is that most of this is all about how we can apply a machine to a specific system. So an electric machine might form just one part of an overall system. So in an electric vehicle, you may have 4 machines, one on each wheel. You may have multiple drivetrains. You may have combustion systems, electrical systems working together in a hybrid. But you need to have ways to actually represent those on an abstract level as an electrical circuit so that you can have something that shows you what kind of power goes in, what kind of power comes out, and you can start to build those into an overall system model so you can apply them. So let's look at one or two of those questions now. So our first question is around what constitutes an electrical machine. And ultimately, it's about transfer of energy. So all machines transfer energy between mechanical and electrical systems. And as we can define from our sort of early years, electrical power in its simplest form is voltage times current. So our voltage times our current tells us what our electrical power is. Mechanical power has a simple expression as well. So mechanical power, mostly you'll be dealing with in rotational form. So torque times angular velocity gives us our mechanical power. Or if we have a linear system, that will be force times linear velocity. So both of those give us an expression of mechanical power, and both of these define in the simplest possible terms what we're doing with the machine. We either have a motor where we're taking in electrical power, voltage and current, and converting it to mechanical power, or we have a generator where we're using mechanical power and converting it to electrical power. So machines can be in two forms. So the most common machines you'll deal with will be rotational machines. It's very, very common that we get rotational machines. You do get linear machines on the small scale. They're used for things like robotics, automation. They're used for machine tools. They're used for things like XY motion. So where you have a machine tool, say a cutting laser that you need to position, you'll have an X and a Y adjustment of linear machines, and those will be able to position that accurately. But the most common things you get are rotational machines. One thing that all of these have in common is that they all have to have mechanical movement between two parts. So this is an absolute fundamental. All machines have to have two parts. One part that's fixed and the other part that's moving relative to it. So why is that? Let's ask a question. Why do we have to have at least one part that can move freely relative to the other part? I'm going to get a book out in a minute. Anyone? Come on. It's all right there. It's all about that motion. So if you look at our mechanical power equations, we have torque times angular velocity, so rotation, or we have force times linear velocity, so linear motion. But to actually get any real power out, we need that motion component. You can't do work if you're not actually having an impact on the environment. You can output force, you can push something, but you aren't outputting useful work. So that means that one of the fundamentals of machines is we always have to have some kind of motion between one component and the other. And that then implies that we need all kinds of other things. We need all kinds of bearing and support systems to let things rotate or to let things move in a linear fashion. But we always have to have that motion, otherwise we don't have one of these key components of mechanical force. We do have these definitions, I mentioned them before. So electrical to mechanical is a motor, mechanical to electrical conversion is a generator, and actually one of the things that's fundamental in machines is most machines can work in either mode. So there are some small exceptions, but what we pretty much find is because we're using the same sort of fundamental set of electromagnetics and the same fundamental rules, we can find that pretty much all machines can work as a generator or as a motor. In simple old-fashioned applications, they usually didn't. You know, if you have a pump, it's often just doing one single job. But what about if you have something like an electric vehicle? You want to be able to do things like regenerate your braking energy. So all of a sudden, it's working as a motor most of the time, but when you're braking, it doesn't really want to burn all that energy into brake discs. Ideally, you want to pull that right back into your electrical system. So all of a sudden, it's working as a generator. And this is supported by the fact that most machines can do that quite happily within certain constraints. They can generate power, they can motor. So why do we have different forms of machines? One thing you will find is that the sort of standard industrial machines all look very, very similar from the outside. So that's an example of a bog standard industrial machine. So it's a round or rectangular body with a shaft sticking out at one end. It normally has some kind of terminal box, thing like this on top, where you connect the electrical side, the shaft there which rotates that you connect the mechanical side. And it's all sort of very, very simple and standardised. And we'll talk about that sort of standardisation in a bit. But you find they look very, very similar. We might see some differences already, though, because you get differences in things like supply. Sometimes you get DC or universal motors, which are supplied from a much simpler electrical system. So supplied typically in DC from a battery. So the simple motors in a car, ignoring the drive motor, tend to be like this, where the simple DC motors powered from the car's battery system and alternator. We also get larger scale, so things like underground trains are very commonly DC supplied. So large electric traction things, these don't have to be small motors, or they could be supplied via a power electronic converter from mains AC. We also have AC motors. So AC motors could be supplied directly from the mains, as we'll talk about later in the course. Some motors, like induction motors, are actually ideal for simple plug-and-play applications, where you can plug them directly into a mains three-phase supply, put a mechanical load on them, and if it's within their capabilities to drive it, they basically will. You don't really need any kind of control, external switching, drives, feedback, anything. They're very, very simple plug-and-play devices. But of course we get the other end where we need close control, where we could have a power electronic converter, a variable frequency AC source, in order to take close control. We get different operating conditions through different machines. The key difference is between induction and synchronous. So we get some induction motors, which, as I said, are very plug and play, and they can produce force almost anywhere within their operating characteristic. We get synchronous machines, which are the opposite. They have to be very, very closely speed controlled, because they will only produce continuous torque at one given speed point, known as the synchronous speed. We also have different operating requirements. So I talked briefly about the sort of advance of modern power electronics. So DC machines used to be actually a big deal and a favourite up until about 30, 40 years ago, basically because of this factor, because we didn't have modern power electronics, we didn't have good ways to control AC machines. So they were good at doing simple tasks, but we couldn't really control them. And this was a real limiter for holding back machines and machine applications. But actually, with modern power electronics, we have kind of taken over this role. So we don't cover a huge amount of DC machines. There is some supplemental material actually on the Moodle page if you're interested, but this is something you might have covered a little bit previously. And you may use some of the sort of control theory and examples, but these weren't ideal machines, so these have mostly been superseded. And ultimately, this is because we have these modern power electronics. So modern power electronics let us control machines more efficiently. They let us get a range of performance characteristics out of machines, but they also let us have things like permanent magnet synchronous machines. So this can be anything. This, of course, can be high power permanent magnet synchronous machines, but actually, if you look at it, something as simple as, say, a DC fan, you know, the kind that you get a dozen of in a PC, the kind that you get in pretty much all household electronics, are effectively permanent magnet DC machines with a tiny little power converter and switching system. So even at that smallest form, we're taking advantage of control methods, we're taking advantage of switching and reliability, and ultimately we're building something that's simple and compact and does the job. But these also enable interesting technologies, so very reliable machines. They allow us to have things like totally enclosed machines, so machines that we can put in dangerous environments, whether that was an explosive environment where we can't have sparks, or something for food processing, or something in a clean room. They let us actually have sophisticated technologies and build machines that can be totally enclosed. And this leads to that thing I pointed out earlier, is that we do get forms of machines that won't operate at all without special power electronic controllers. So these typically require a control. They require a pulsing on and off of the supply to their phase windings, usually based on feedback of position. And this is something that, again, even those small brushless DC fan motor type things, they actually have this kind of system. They have small Hall effect devices that pick up the rotational position of the fan, and they use that to determine where they put the currents and voltages in the windings. So even at that small, very basic level, we're still taking advantage of these skills with very, very simple power electronic controllers. And ultimately, the other thing we find is that different motors have different characteristics. So we don't have one single plug-and-play motor that's the best at every job. So we find that all kinds of motors have different characteristics. They have different characteristics around temperature, cost, efficiency, and so choosing machines for a particular application can be very challenging and very difficult, because you've got to balance all of these factors. There's no point having a machine that's the best possible machine in the world at doing a job if it's so expensive that no one can afford to do a job with it. So there's a huge array of differences in terms of what machines we have and why we choose them. So just to try and illustrate the variety of available machines to you, this is a figure that was done a few years ago showing the range of power levels in electrical machines. And you can see here we have 10 to the minus 6 up to 10 to the 9 watts. So these all represent individual machines. So this is talking about the smallest sort of micro movement electronics and watches, up to things like huge large scale power generation. In terms of torque levels, so the actual force they can produce, again we have a similar range of torque level, and these represent sort of the finest little electronics PCB drilling motions up to huge mechanical traction drives, up to huge mining rigs driving enormous forces. We have machines that range from 1 to 10 RPM, very, very slow speed, up to super high speed. So things like 500,000 RPM, which is a typical speed for, say, a PCB spindle drill. So something that's working in a chip fabrication plant, drilling very accurately, very fast, 500,000 RPM. And on the other side, of course, we get things like wind turbines, which are down to 10 RPM, 1 RPM, sometimes even less, so very slow rotations. Then positioning accuracy. So this is an interesting one, because in a lot of applications, it doesn't really matter. With a wind turbine in rotation, you don't really care about position accuracy. In other applications, so things like accurate positioning robotics, you can have massively high demands on positioning accuracy. So machines can also get positioning accuracies down to the nanometer, depending on the particular machine. But all of these are using the same fundamental technologies. They're using the same underpinning electromagnetics and behaviours in order to meet these applications. So let's look now about topologies. And we have 3 generations of machine topology that we're going to look through. So I talked about those DC machines. So those were the first type of machines. Those were invented over 150 years ago, but they've mostly been superseded, except for the sort of edge cases and the small electronics. The main ones we consider in that generation are induction machines and synchronous machines, because these are still a huge topic. These are still used in the vast majority of applications today. Then we go into the second generation, and these are our permanent magnet machines. So these are permanent magnet machines, and the enabling technology ultimately in these, as you'd expect, is better permanent magnets. So as better permanent magnets were invented, as we got things like neodymium ion boron magnets that have very high energy and power densities, all of a sudden we could do much more useful things with permanent magnet machines. and we started to get permanent magnet DC machines, but also permanent magnet AC machines for increased power densities. And then finally we reach the more modern generation, control-reliant machines. So these are all enabled, as you would expect, by better drives and control, by power electronics that let us control the supply to these machines to be whatever we want it to be. And these are our brushless permanent magnet AC and DC machines, and also the reluctance machines that we'll talk about at the end of the course. But each of these has been driven by a step change and improvement in available technology, and each of these has allowed us to do more and different things with our machines. And these are just some examples going from the most simple type of machine up to the most complex. So going from our most basic induction motors and DC motors, which have been around for hundreds of years, up to our newest generation, the switch reluctance motor, developed 40, 50 years ago. So we have a few remaining questions. So what do you need to know to use a particular machine type? How can you work out the method of working of a machine? So this is where we'll start to diverge the course. So we'll be doing machine basics and magnetics over the remainder of the course, but we'll also be focusing into particular machine types, talking about them both in terms of fundamental characteristics and how they compare to other types. So we're going to take a little break here. So we'll start again at 3 o'clock. In the meantime, there's a few simple quiz questions there. So these are all things that hopefully you should be able to have some idea of if you've done these in years 1 and 2. So there's no absolute obligation to do this. I'm not taking scores, but just have a look through these. Are all of these concepts familiar? It's a good sort of overall guide to say, are you fairly familiar with the concepts we're going to be using over the rest of this course? The concepts around power, around torque, around three-phase and single-phase. So have a look through those, and we'll take a break obviously as well if you want, and we'll restart at 3 p.m. Thank you. Hey. Okay, so I'll restart the recording. Please keep an eye on these. Occasionally they can catch us out, so obviously trying not to leave recording switched off, but it's easy to do. So if you don't spot me putting the recording back on after a break, just let me know. So these are the answers to our quiz. Again, these are all things and concepts that you should have hopefully dealt with in prior years. Don't worry too much if you didn't quite recognise these. So I will be recapping these a bit, but also just take the time to look through these. They're fairly fundamental concepts. So the concepts around power fundamentals for a motor. So we have our output power, which is our real power actually converted and delivered to the load. So if this is a motor, it's doing mechanical work, so this would be the mechanical power output for a motor. The input power in this context would then be our total supply power, so our total volts and amps required to operate. So that's going to include everything in terms of input power. It'll include both the real part of the power that's doing some kind of physical work, and it'll include the reactive power, which is getting stored in the energy storage components, which for typical motors are going to be inductances. Then we have the concept of power factor, and this is how we split off those two parts of real and reactive power. Our power factor represents the proportion of our input power that's actually going into real consumed power. We don't know if that's all converted power, that could be output, that could be losses, typically it's a mixture of both. But the power factor lets us work out what proportion of the power going into our machine is actually converted rather than just stored energy. And then efficiency is the final part of this puzzle, because efficiency lets us work out how much of the power our machine is consuming is actually delivered to the load as output power. So that's output divided by output plus losses. So we generally define efficiency as a percentage. So say we're supplying 100 watts of real power into a machine with 10 watts of losses, our efficiency will be 90%. So out of that 100 watts supplied, 90 watts goes to your output and the other 10 is losses. The factor that relates three-phase to single-phase is this root 3. So regardless of if a system is connected in star or delta, what we find is that from our overall characteristics, we have a root 3 that actually governs the difference between per phase values and our total. We have power as an overall equation equals T times omega. We mentioned this earlier in the course. So our power is equal to torque times velocity in terms of mechanical power. And then looking forward, we have this ideal governing equation. So this is something we cover in first year for our undergrads, where we have an ideal equation that says torque is equal to a factor at its most, that can be 2 for an ideal machine, times the air gap volume of a machine, times our flux and current loading. So those two are limiting factors, which means that actually what we find is that torque and power ultimately go up in proportion to volume, and our power goes up in proportion to speed. So we have some strict governing factors on the physical characteristics of our machine. So just a very quick go through, and as I said, don't worry too much if you can't quite remember all of those, because we will be recapping those and covering them in next week. So for our final part of the lectures, we're just going to look at some real-world applications. So we're going to be looking at some of the actual applications of machines. So how these machines are actually used. We'll talk a little bit about what type of machines are used in each application, but also why they're used, just to try and illustrate this process of choosing machines to meet a given application. Here we go. So the first application we're going to focus down on is electrical and hybrid vehicles. So I talked a little bit before about how electrification, both in terms of hybrids and full electric vehicles, has been a huge growth factor. And it's all about efficiency, environmental impact. It's all about ultimately, if we can move these to full electrification, we can increase efficiency, we can reduce energy use, and we can also reduce emissions, especially localized emissions from traffic. There's a lot of different types of machines to use for traction, and one of the interesting things is that the automotive field pretty much uses every possible type of electrical machine you can think of at some point. And even companies like Tesla have moved between various types, including induction motor, brushless DC and AC machines, and switch reluctance machines. So it's very common that different types of machines are selected, and this makes up a complex pattern depending on where you mount the machines. Now, one of the key things about electric automotive machines is that you have a hugely demanding torque speed characteristic. You need to be able to provide a lot of torque and a lot of acceleration at low speed. You also need to be able to cruise along at very high speeds. You have a very demanding operating environment. Depending on where we mount those machines, they could be something like the top left image where we've got a wheel drive machine, and in a wheel drive machine you have no effective suspension or protection for the machine in your wheel. And what that means is, whereas you get a nice smooth ride in a car because you've got all kinds of suspension, if you have a wheel drive machine, it doesn't have any suspension. Any bumps in the road, any impacts on the tyre, all get transmitted to the machine. You need a very, very robust machine that can withstand that can withstand all the dirt, the road mess, that can also withstand things like corrosion from salting roads. There's all kinds of challenges there. If you move your electrical machine into a different place, if you put it into the engine compartment, you just end up with a different set of challenges. It's no longer exposed directly to the road, it has quite a lot of protection from the suspension, but you're sticking it into an environment that's ambient temperature is close on 100 degrees. You're sticking it in there with all the heat, with the mechanical vibration, with all the sort of grease, with the risk of cross-contamination from hybrids with petrol. There's all kinds of challenges. So let's look at the range of applications for electrical machines in cars. So what's the most common electrical machine that we get in cars? So anyone want to hazard a guess about the most common electrical machine we get in cars? It's a good guess actually. Pretty much all cars have a dynamo. They have an electric machine that's actually taking some of the mechanical work and feeding it into the electrical system. But we typically have even more than that. And the place we tend to get these, the place where we see in a traditional car the most machines, is the analog gauges. In a typical car, 3 or 4 analog gauges. An analog gauge is an electrical machine. It's the simplest possible form of electrical machine. It's typically something as simple as a coil of wire and a magnet, and depending on the current that's going through your coil of wire, you get a repulsive force on a magnet that pushes it this way, and you have your gauge attached here, which is what's showing you whether you've got full or empty fuel, or what your RPM is, or something else. So even in the olden days, we had all kinds of electrical machines through cars. But of course, dynamo is a very good guess, because that's sort of doing useful work. So the dynamo, the electric system, and then coupled to that is the starter. One of the reasons that combustion cars took over from the old electric vehicles of the 1800s was when electric starters got introduced. Because to start up that combustion engine, you actually have a little electric motor that turns it over and kicks off the combustion process. Without that, it doesn't start unless you do the old sort of Victorian thing of having a car with a crank on the front that you turn round. So the electric motor actually replaced that mechanical cranking process, and so sealed the doom of the electric car in the 1880s. And then, of course, as we said, the dynamo or alternator. So that's in pretty much all cars. We're not even talking about electric cars yet. The alternator or dynamo is where you're generating off some electrical energy from your mechanical train so that you can feed that battery, both to store energy to feed your starter in future, but also to feed those sort of light loads to feed the onboard electrics and other things. So only then is where we start to get to the more modern applications, the more modern alternatives. So things like traction drive motors. And as I've said, as this goes on, we get more and more electrification. So I think electric and hybrid vehicles will just about be gone by the time I retire, but by the time you begin your careers as sort of engineers in a year or two, there's going to be about 6 to 11 years before we don't make combustion vehicles anymore. So this is really something that's coming very fast, and it's leading to huge uptake in electrification in drivetrains. And then, of course, this isn't the only thing. We also have electric loads in other interesting places. So in things like turbocharging, so even things like diesel engines, one of the things they tend to do with them is turbocharge them. They pressurize the exhaust using another electric motor and feed pressurized air in to improve the performance of the machine. And then, of course, there's all kinds of other things. So as well as all these things, you look at a modern vehicle, it's got machines and motors absolutely everywhere. It's got electric windows, it's got electric seats, it's got solenoids and electric locks. So even taking a vehicle from the old traditional vehicle up to the brand new, we get machines absolutely everywhere. But let's focus on the actual drivetrain and the traction drive, because a lot of those things like alternators and things are very, very sort of traditional, they've been around for a while. But looking at the traction drive, that's the real challenge. And the challenge is all around in those drive requirements. It's all in the need to have things like high top speed. So the top speed of a machine, depending on where it's mounted, can be anything from 3,000 to 14,000 RPM. And the reason for that is all about gearing. So one of the things you do find in automotive electrification is there isn't even a consensus on where you put the motors. We have people doing everything from putting the motors in the wheels, to putting the motors on either side of a gearbox, to putting them coupled to the combustion engine. But this changes the requirements quite a lot. If you have a motor in a wheel, it's got to go very, very fast, 14,000 RPM. It means you can make it smaller because of that link between rotational speed and power density, but it has other challenges. Or you might couple it directly to your combustion engine type drive shaft, and it'll be going at a few thousand RPM and then feeding a gearbox. So there's big differences in speed requirements. And of course, this also means, as I said before, because we have this relationship between our power and our speed and our volume, it means that actually the volume of the machines varies hugely. The size of these overall machines needed can change by a sort of ratio of 5 to 1, depending on if it's a wheel drive or if it's mounted in the main engine compartment before the gearbox. Now, one thing we're going to pick out just as an example is Freedom Car. So Freedom Car was basically a target specification for automotive electrical machines. So this is something that was come up with as a sort of project working between industry and universities. And the idea of this is these are the specifications you need for an electric motor if it's going to really, really be competitive with combustion engines. So these are the specifications you need to give it to actually do that job and to be a viable competitor. So you can see we have requirements around rated power, so the typical power it's going to be putting out most of the time, but it also has significantly higher peak power requirements, reflecting the fact that sometimes in a car you need to put your foot down, you need to get a bit more power out, so you need a short-term power delivery in terms of both power and torque that will be significantly higher than the average. You'd have different maximum speeds depending on where you're intending to mount this. It could be, as I said, anywhere before or after the gearbox. You have to operate at typical voltages within the sort of, as we call it, the low voltage range. So you can't have thousands and thousands of volts because it's impractical in a car type power system. You have to have some practical limits on current, and especially practical limits on things like sizing. So again, you have real physical limits where you can't make your machine enormous. You can't take up the whole engine compartment with a massive electrical machine. It's just not viable. So you have real limitations of how big a machine can be to do this job. And by that same token, we also have limitations around the volume and weight of this. You have fairly standard cooling. Now, one of the advantages of automotive electrification is we always have these very good cooling systems in cars because combustion engines already need a lot of cooling. So we have a long established cooling system of sort of radiators and pumps and liquid cooling. And this is an advantage in some circumstances because it tends to be better than air cooling, but it also means that you have to be able to adapt, especially in hybrids, to a cooling system that's designed for combustion engines. So the typical coolant temperature can be over 100 degrees C in a combustion engine. So actually having a coolant that's already running at 100 degrees C is a real challenge. Then we also come to things like efficiency. So again, if we want these to be viable, if we want them to be competitive, they have to be efficient. So they have to have 90 plus efficiency over the vast majority of the speed range to be useful. And then of course we get into the real things. So things like technology and unit cost. So technology is basically saying that we prefer not to use rare earth magnets because although they give us the best possible solution, they're expensive, they're still quite hard to procure outside of certain markets. And ultimately, it all comes down more than anything to this, because if electric cars are going to take over, the price of a car can't suddenly go up by 40 grand. It will cause a huge economic shock. So what it really means is that they need to be mass producible, they need to be realistically costed, so that electrification can genuinely take over from the combustion motor. So let's talk about another application now, generation. So generation is an interesting one because this is one of the most long-standing uses of electrical machines. So almost all forms of generation use an electrical machine. So the only real form that doesn't is solar. So solar is using photovoltaic conversion, feeding through converters direct to the grid, but it's a very small part, especially on the UK grid. So pretty much all forms of generation are using electrical machines, whether it's your most sort of traditional coal-fired power plant or a modern offshore wind turbine. Now, we generally, in all of these applications, want the thing to be working as fast as possible because we come back to that fundamental governing equation, power equals torque times velocity. But that's massively application dependent. If we have a nice sort of steam turbine, that's going to be running nicely, and it's actually going to be rotating any steam turbine in the UK at exactly 3,000 RPM. And that's because they're all synchronized to a grid going at 50 Hertz. So there are simple relationships between the rotational speed of generators and the frequency of the output, which means steam turbines tend to go at this sort of nice fast speed, which feeds very well into this power equals torque times velocity equation. Now we don't tend to get 3,000 RPM from wind turbines, we tend to get a few RPM. Large wind turbines rotate very, very slowly. And it's a real fundamental challenge because it massively impacts the power density we get. It's a massive challenge in terms of how much power we can get out of a wind turbine. Whereas a modern wind turbine can output a few megawatts, If we look at a similar sized generator in a power station, we're looking at easily sort of tens, hundreds of megawatts of power from the same volume. And it's all down to this speed differential. So the range of applications. So I've talked about how we have these conventional fuel burning type things. So these are just generally combusting of fuel. So traditionally this was something like coal. More modern combustion tends to use gas. But it's converting thermal energy by burning it, by heating water into steam. That steam goes into a turbine to give mechanical rotational energy. And then we couple that to a generator to push electrical energy into our grid. So wind turbines do a similar thing, but they get rid of that conventional combustion step. They just have a direct rotational thing between the rotor and the machine. But most modern wind turbines still use a gearbox. And that's how they try and get around this expression. Because our power is based around rotational velocity and volume, it means a couple of things. So if we include a gearbox in our machine, as our power is proportional to volume and rotational speed, we can either get more power out of the same size of machine, or we can make our machine smaller and lighter, and often make it cheaper. So if we want to have a wind turbine, we can actually take advantage of things like gearing in order to get this to be a better, more useful machine. Now, hydro is another interesting one. So hydropower, it's a little bit of the UK grid. It isn't a great deal, but if you look at some countries, it's a huge part of the grid. If you look at Brazil or China, say, they have huge hydroelectric projects which are putting in huge amounts of power. But in most of these situations, what you find is they do actually use high-speed generator. What they tend to do in these is they use pressure from the water in order to still operate something like a Francis turbine at around 1,000 RPM. So although they're using water, it's quite far away from the traditional sort of water wheel type approach. They're using pressurized jets of water to still get reasonable speeds because, again, you're looking at generating as much power as possible. Your weight isn't really an issue, your volume isn't really an issue, so you want to get as much rotational speed as you can. So in terms of conventional generation, this is a good little illustrator because it shows you some of the differences between traditional and renewable generation. So if we're looking at a generator to be coupled into a steam turbine for a conventional plant, we're looking at a few key characteristics. It has to be high efficiency. We want to get as much as possible out of our system, so it has to be a very, very efficient machine. We want it to be reliable, so we don't want it to fail all the time because it's feeding into our grid, but we can rely on maintenance. This is something that's going to be in a nice big generator shed. It's going to have a team of technicians around it. It can be constantly maintained, it can be checked, it can be taken offline for scheduled maintenance without too much trouble. It has to produce high power and high power output. And the typical kind of constraints we have on these are things like system cost and lifetime. Ultimately, the conventional generation plant, we need to have it keep to a certain cost, we need to have it last a long time, but it kind of has an ideal environment. They also have challenges around starting and synchronization needs. One of the big challenges around the grid is how we actually couple new power plants in. I talked before about how all of these power plants are running at exactly the same speed with the same frequency. And we do have some challenges of, if you want to connect a new generator to the grid, you have to connect it very carefully, or the whole thing will just tear itself apart and catch fire, trying to synchronize and absorb energy from the whole grid at once. So we have issues around starting and synchronization, and we also have issues around things like faults. So if you get a fault on a major part of a power system, if a big chunk of a country's grid goes offline, it's often a business of sort of hours, days, sometimes even weeks to get everything back operating. Because a lot of generators, what you find is they actually need power to produce power. We have some generators designed for what's called a black start condition, where you don't need any electrical power to make them work, but the typical generator we get on our grid can't generate without electrical power. So if a local part of the grid goes down, you can't even start generating in the first place. So there's big challenges around that. We also have to design these to be dispatchable. So it's all around control and idling operations. So there's no significant energy storage on the UK grid or on most national grids, which means you're actually trying to constantly feed in the same amount of energy as you take out of the grid. So it's a huge balancing act where you have what's called sort of spinning ready type generators that are just sitting there rotating but not producing any power, so that you have that power capability, and if you need to switch that on in seconds you can do so. But ultimately, one of the good things about these is a generator for conventional generation has pretty much the ideal environment. We have a custom designed space, we don't have tight size or weight limits, we have ready supplies of cooling water, we have people around them to make sure they operate. So let's compare this now to renewable generation, because ultimately this is a hugely expanding area. As I mentioned before, renewables has become a massive part of the UK power grid. In fact, on the right day, wind power renewable will be the chief source of energy on the UK grid. And we use a lot of different machines in this. So once again, it's a bit like automotive. There's all kinds of concepts and all kinds of ideas of what we do. We have different types of machines, some of them quite exotic, induction machines, some synchronous machines, some using permanent magnets. There's different technologies. And of course, some of them, as I mentioned, use gearboxes, others try and avoid that. But one of the main things straight away in renewable generation is that reliability and maintainability are massive parts of this, especially for offshore generation. If you have a generation plant that's just sitting in the middle of Nottingham, like the one 10 miles down the road, it's easy to sort of maintain and repair and fix things, to put in new parts, to do whatever you need. If you have a wind turbine that's in the middle of the North Sea, repairing, maintaining, fixing that is a huge problem. It's a huge logistical challenge. So reliability and maintainability are massively important for offshore generation. So the typical requirements we have for these are very high reliability. As I've said, you don't want it to fail, so you want it to be very, very reliable without too much support. Again, you want it to be efficient. You want to get as much power out of that system as you possibly can. You want to have high overall power levels per turbine. You'd much rather generally build one larger turbine than 10 smaller turbines, which implies that you want to get as much power as possible out of each individual turbine. You want them to be low maintenance, so this is slightly different from the reliability. This is more around, you know, if you have a generator that's somewhere in a power plant and someone has to go along and grease all the bearings every week, that's not a problem. If someone has to take a ship out into the middle of the North Sea and climb a pole in a storm once a week to do that, it's more of a challenge. Now, the typical constraints are often around things like weight and size, because of course a wind generator is something that you're putting up on top of a pole 50, 100 metres up, so it has to be very, very carefully constrained by weight and size. And that's of course an issue with onshore, but even more of an issue offshore, where any of these have to be actually mounted into the seabed. The location environment itself are hugely challenging. If you're building an offshore wind plant, it needs to be able to withstand absolutely crazy weather. It needs to be able to withstand huge and heavy winds. It doesn't need to generate in those conditions, but it's about physically surviving. It's about not having a storm come through and rip out your billion-dollar wind farm. It also needs to have grid connection. So if you've built an offshore wind generation system, great. How do you get all that power back to land? You need a complex system of power converters, subsea transmission cables, and even once you get to land, you still need to transmit that power to wherever it can couple most usefully into the grid. And it is a very, very hostile environment. So fundamentally, we're designing for something that's a much more hostile, challenging environment. So let's look at industrial drives. So industrial drives are a very different area. So industrial drives are basically a very, very typical bog standard mass-produced commercial drive. So these are the standard drives that we use in a huge range of industrial applications. So going forward as graduate engineers, these are the types of machine and drive you will most typically use. So taking something like that, that's a very, very standardized electrical machine, and putting it into an application to drive a fan or a pump or a machine motion or something else. And these are a standardized type of drive used across industrial applications. One of the things you'll find is that these are pretty much standardized and mass produced. These are effectively catalogue items. So if you want, say, a 15 kilowatt drive for the UK, you could go to one of probably 200 manufacturers and they will have a standard 15 kilowatt, three-phase electrical machine, and they'll all have a very similar footprint, they'll all have a very similar mounting type, they'll be competing on things like efficiency and performance and reliability, but these are to some extent standardized, so they're the kind of thing that you can buy in as a finished component and integrate into a larger system. There are still a huge range of systems available dependent on application area, so everything from the fairly simple bog standard industrial drive to fairly complex controllable systems to machines designed for specific applications, explosive environments. But they aren't typically too application specialised. The whole concept of these is that this is a machine that can do a job, and you can specify that job in terms of a mechanical output. It needs to give a torque at a particular speed, but they're not specifically designed to an application. These are the things you would buy in to put in as a sort of non-specialist application-focused engineer. So these are the things that are working on all these different loads that we talked about: fans, pumps, machine tools, robotics, conveyors, lifts. They're all over the place. This building probably has a couple of hundred in them easily. And these are just the standard machine type things. So the requirements we have around these, the typical requirements you get are these tend to be standardized around output power. So as I said, you tend to have machines that are 15 kilowatt, 50 kilowatt, 90 kilowatt, whatever you want. They tend to have a sort of standard power. They'll be based on a fairly simple grid supply. So they'll be based on either the European or US grid, which are two fairly fixed standards. So that's a three-phase grid at either 50 or 60 hertz, depending on Europe or US, and 400 or 480 volts as standard. Again, Europe or US. They'll have a given operating speed. So induction machines can operate at all kinds of speeds, but they'll generally have a given speed which is their optimal performance range. The typical constraints we get are things like environment, so this can range from standard environment to things, as I said, like fully enclosed for hazardous, corrosive, clean room type applications. They have very, very high efficiency standards. So what you'll find on machines is they have very, very strict efficiency standards. As I've said, these are internationally mandated requirements for how efficient a machine has to be so that it's using as little energy as possible. And they also have standardization around frame sizes, and that's to let you interswitch them. It's so that we can treat these as a sort of product, just like you would a piece of electronics or a resistor or anything else. Nominally, a sort of 15 kilowatt machine should go into that frame size, and you could go and get one from a different manufacturer, switch it out, and get the same kind of performance. Now, looking at a couple more transportation applications, electrical machines are also used a lot more in marine applications. So this is a concept that uses podded thrusters, so moving away from the sort of traditional, I like to think of it as the sort of Titanic model of you have a nice engine room with a nice mechanical plant, and that's turning a rotating screw that goes out the back of your ship. So modern marine applications are really, really pushing machines, drives, because it really increases what they can do. So by using a series of electric podded thrusters mounted around the ship, it massively increases usable space because you can distribute your engine systems into where they're most efficient. It completely decouples engine speed from propeller speed, so you have active control of all your propellers. You have different propellers that can face in different directions, work at different speeds and powers. It gives you faster dynamics, so if you think about something like, say, a cruise ship or a cargo ship where it might have some complex docking manoeuvres to do, if you have a system of podded thrusters around a ship, that ship can literally spin on its axis. You can do some incredible things. We've even had sort of things where, when they first introduced these into cruise ships, quite commonly cruise captains used to break them because they used to sort of show off and do things like the equivalent of a ship version of a handbrake turn into ports. But these are letting you do all kinds of dynamic things. And they optimize your power use. Rather than having a generator that's running at whatever speed you need in order to run the propeller that's directly coupled, you can have a nice, efficient, high-speed generation plant tucked away, and you can supply whichever propellers you need in the most optimal power configuration. So looking at these, we have things like, as I've said, the podded thruster, and this completely decouples our electrical generation and motion without needing mechanical connection. Marine applications do also have some other electrification things. They also have smaller loads, so things like bow thrusters and pumps. Again, it's a bit like electric vehicles, where although the sort of actual drive system is the thing that's a real driver of this today, historically we've had a huge amount of distributed electrical loads throughout ships, taking the form of, again, those conventional motors, fans, pumps, and so on. They also give you active control. You can do things like control of steering, and you can take active control of a ship. And finally, marine applications let you do things like emissions management. So in certain areas of the world, you have to be very, very careful of your emissions. You know, say you're taking, again, going back to the cruise ship analogy, if you're docking a cruise ship into Venice, you can't just be pumping out a load of smog and a load of diesel fumes. So having a hybrid type electric vehicle lets you control your emissions and actually output a much cleaner sort of energy profile depending on where you are and where you're operating, making sure that you don't pollute areas of special interest and things. So the requirements of this are interesting. We're taking an electrical machine now and we're putting it under the sea, built into a sort of thruster pod. So our challenges are a little bit like wind turbines, and these have to be very robust and reliable with a long lifetime because they're not easily serviceable. If you want to really repair and fix one of these things, it's a huge job. So once again, these need to be massively reliable with a long lifetime. They need to be efficient because the whole point of this electrification is to save energy and to reduce your fuel use. You need to have a high degree of control so that you can use these to control your overall vessel. And they also need to work, typically with large mechanical gaps. Something like this, you need to design it in such a way that it can actually withstand a reasonable amount of sort of sea debris and rubbish going through the propeller, which means you actually have to push your magnetic field across fairly large gaps typically. Now, the typical constraints, as I've said, you have very limited access, so they need to be very reliable. You also have challenges in this case around seawater. So seawater is extraordinarily corrosive. It's very difficult to have machines that operate for a long lifetime under the sea. So in many ways, it's kind of like the wind turbine application, but even more challenging. And of course, the other challenge is cost. Take-up of anything like this is ultimately based on the cost of the system. So we're going to highlight two more applications. So the first thing we're going to talk about is more electric aircraft. So this is a big area of research right now. You may have seen news articles on this because this is something that's really getting pushed. Because we have some fairly good technologies for automotive electrification. We have pretty high-performing electric cars now, but we still don't have anything like an electric passenger jet. There's a real challenge still around actually getting electric passenger jets. There's huge benefits there because we can introduce much more efficient systems. Electric motors are more efficient than than the sort of jet propulsion, but there's huge challenges. We have challenges, especially in electric aircraft, around fault tolerance. So the fault tolerance standard for aircraft is one failure every sort of 10 to the 9 operations. So that's kind of the level of failure you're looking at. It pretty much has to never go wrong. And actually getting electric machines and electric drives and all the associated parts to that level of tolerance isn't easy. Whether those are direct drives, so driving the aircraft, or whether it's electrical systems driving control surfaces, so rudders and flaps and things. But electrical machines, once again, are used for a lot of electric loads on aircraft. And electrification isn't just all or nothing. One thing we find is that modern generations of aircraft have much larger generators, much larger electrical loads, and they're moving away from the older systems they used to have, things like hydraulic and pneumatic lines that used to control a lot of the secondary surfaces and things. So we have all kinds of challenges on board an aircraft. So we have challenges around propulsion, we have challenges around generation. One thing that I always find interesting is pretty much all aircraft actually have something like this on board, a ram air turbine. And this is actually a tiny little deployable generator designed so that if your power system goes out, you can switch it back on. Remember how I was talking about losing power on a grid, how on the sort of national grid level, if we lose power on our grid, we often need power to put it back on. It's the same on an aircraft, except you can't plug it into anything. If your power system happens to go out mid-flight, how do you get electrical power to restart your electrical systems, to restart your control systems, to get things moving again? So pretty much all aircraft have something like this on them, which is actually just a wind turbine. It's a tiny little wind generator, but it's designed so that you can deploy it manually so that if your electrical system goes out, it can generate just a few kilowatts, but enough power that you can actually get your aircraft operational, that you can power your avionics and keep things moving. And as well as that, of course, as I've said, we have those generation and propulsion loads. We also have things like control surfaces, so being able to use electrical systems to control primary and secondary, to operate landing gear, and also things like green taxiing. So this is something the University of Nottingham actually developed a few years ago. So having an electric motor built into the nose wheel of an aircraft. So instead of taxiing aircraft around an airport runway, moving them from sort of gates to runways by using the jet engines, kicking out huge amounts of pollution very inefficiently, having an electric motor built into the nose gear of an aircraft that can actually drive that aircraft around without using the jet engines at all. So the key challenges around these, for example, of the inbuilt generators in a jet engine, are things like having these being small and light. So the typical aircraft generator is actually built into the jet engine. So one or more of the jet engines has a generator built into it so it can generate electrical power off of the rotation of the engine. And these typically work as both starters and generators. So when the aircraft doesn't have the jet engines running, it'll rotate it up to speed so that you can get that combustion going, and then it'll switch to generator mode to feed onboard electrical loads. So in order to do this, it needs to be small and light because it's embedded into your jet engine. You need to have very, very high efficiency and high reliability because, as I've said, it pretty much cannot fail in any practical timescale. But it also has a constrained environment. Imagine having an electrical machine that you have to put in the centre of a jet engine where you're combusting jet fuel up to 1,000 degrees plus. It has to work anything from a full to a quarter atmosphere of pressure. It has to be put inside the heart of that jet engine in a place where it can still function and not affect the behaviour of the whole thing. So even not looking at the full sort of electric propulsion, there's huge challenges around how we build and embed electrification into modern aircraft. And above all, we have these challenges around size, weight and reliability. We need these to be small enough, light enough and reliable enough to make it onto aircraft in the first place. So looking at the final topic we'll talk about, because this is a little different, I talked about linear motion initially, but I haven't really highlighted any of the applications so far. So linear motors are something you'll get to accelerate a vehicle linearly along a track. So these are something you see in transportation systems, in maglev systems. You also see them in amusement rides, so things like launched roller coasters, as well as things like UAV and aircraft launch. So this is actually what I used to do. Before I was an academic, I used to develop high-speed launch systems. So the example on the bottom left here is a UAV launcher. So the idea of this is it can launch something like an unmanned drone, half a ton of UAV, up to about sort of 50 meters a second in 0.6 of a second. So the idea of this is you can mount that on a tiny little strip of an airfield on the back of a destroyer or something, and you can launch drones over a very, very short space of time. And systems like this at a higher scale are used on things like the US carrier program to actually launch F-35s, so 30 plus tons of aircraft at 80 meters a second over 3 seconds. So these are a slightly different application because in applications like this, you're moving very much away from things like efficiency. You almost don't care about how much net energy you use because you're really focused on high force density over short-term output. You still want a machine that's reliable and robust. You care about efficiency only in so much as all of the energy you provide has to be supplied over a very, very short time. So something like a UAV launcher, it has a whole bank of capacitors, of active power factor correction, of spinning energy storage in order to provide that energy over a very, very short space of time. So you need to focus in on how you actually provide that energy in the timescales needed. So these aren't just used for high-speed launch, these are also the kind of things that are powering baggage transport and conveyors. They are used in some maglev systems, both typically in China and Japan, 1 or 2 in Germany. They are potentially going to be used in Hyperloop if that ever becomes a viable thing, but I'm not entirely sure myself. And then they're used in amusement ride launch and things like assisted aircraft takeoff. And at the higher end, these are exactly the same technologies that are used in things like projectile launch and in railguns, where you're launching at very, very high velocities, thousands of kilometers per second, muzzle velocity type applications. But the idea of these is they have a few key requirements. You need a very high short-term thrust. Because you're looking at a very, very high force, you're then looking at focusing all around force production over the short term. You do need them to be highly reliable because they're doing a very specific application. They need to be fail-safe, especially for something like a carrier launch. You can't have a standard of, oh, every 6th plane just gets flung into the sea because the thing fails halfway through. So they need a high level of reliability similar to an aerospace machine. You need them to be efficient and high power factor because all of that power is coming from an energy store. And they also need to be highly controllable. Something like a carrier launch system needs to be able to launch a half-ton drone or a 30-ton F-35 and still be able to do the same thing and to basically not squash the pilot of the F-35 and not smash the drone to pieces. The typical constraints we get for these are things like power supply and size. Because we need huge amounts of peak power, we need to have a power supply that can provide that over a very short term without failing. We need to have strict limits on what they can do, we need to be able to control them, and we also have limited space and mass, especially for things like carrier launch systems. And then finally, I'm just going to show you an example. So this is showing you the active testing of one of these systems. So this is the US carrier launch system doing initial testing. So you can see that isn't much of a plane, but that's actually a dummy load the same weight as an F-35. So this is the modern form of linear launch. This is the new US Navy carrier with electromagnetic launch system. And this system is designed to launch an F-35 over about 3 seconds up to 80 meters a second. Looks like a lot of fun, doesn't it? So there we go. So these are all our different motor types, and hopefully I've given you an idea of all the different applications of machines, all the different things you can do with machine technology. So thank you for coming in. I think that's about enough for today. So